recorded. So now you might be wondering, so what is gradient and why do I need to compute gradient? But you got some kind of big picture, right? You know, some idea at a high level. Using gradient, you can find out the direction, right? You can get down from the top of the hill to your downhill with the proper direction. You need to have the proper direction in order to reach from point A to point B. You need to know the direction. In order to know the direction, we need to compute the gradient. There is an equation for the gradient. So how the equation got derived, right? What is the underlying principle? That we will take a look at it, and why we need to, how we are going to update this one, how this gradient is helpful in terms of how this gradient as well as the learning rate is helpful in terms of finding the next step size. Okay, in the case of linear regression, we know what is the equation. See, I just slightly changed the notation here, otherwise it is same. Okay, but most of the machine learning practices, if you see, they literally go by this kind of notation. Okay, y equal to the mx plus b. Here the c is the intercept, but here instead of c, I just use the notation theta naught, and y I call this a state of x. Why? Because in the case of linear regression, we have a linear hypothesis function. We define it with state of x. State of x and is equal to theta naught plus theta 1 is your slope into x. Okay. Now, what is the goal of gradient descent? We know we want minimizing the cost. So what is the cost? Cost is, we know very well. So 1 by n, I equal to 1 to n, actual minus predicted and whole square. This is what your mean squared error, right? So you square the, you find out the difference between is the actual and predicted, and then you square it, and then you sum it, and then you find out the mean, right? This is what your mean squared error. But I just mentioned the same metric in different with different notation. Here j of theta. Look here, MSC is equivalent to, instead of JSC, I just say j of theta. So you write j of theta is equivalent to, so 1 by m, same thing. Okay, and here, what is y? So y is nothing but, the right side of thing, right? So here, the right side of thing is nothing but h of x. If I say h of x, the predicted value, it will be slightly confusing. Don't get confused. Okay, because this is the notation has been used by most of the machine learning practitioners. That's why I want you to be familiar with this notation. Hence, I use this notation. Okay, so here h of xi is nothing but the predicted value, because the right side of this one will give you the predicted value, because once you know the intercept and slope, and if you plug in this here, you will get the predicted value will get stored here, isn't it? So hence the h of x, your predicted value. So that's what here slightly have, we have rewritten like this. The predicted value is nothing but h of x and minus yi. Y is your actual, predicted value minus actual. So actually, if you do it actual minus predicted and predicted minus actual, and here you are squaring it, right? There is not much difference, but this is the how they use the notation, right? So j of theta is nothing but your cost. Because using this function, we can find out the error by finding out the difference between actual and predicted, and when you square it and divide it by m, you will get the mean squared error, which is nothing but the cost function. So what is the goal of gradient descent? We wanted to minimize the cost. Okay. Anyhow, I'm not going to discuss all the things. You will get confused. That is not required also. Okay. And the next thing is we will take a look at, how we will find out how we can, derive that equation. Okay. Okay, so what we do is we take the partial derivative on the data. 1 second, I just See, I just write it down here. What is my cost function? J of theta is equivalent to 1 by m. And for the sample from starting from 1 to m, for each and every value, you need to sum it. And h theta of x ith value minus yi. This is my cost function. Okay. See, this is nothing but MSE is equivalent to 1 by m, I equal to 1 to m, and here actual minus predicted value square. That's it. Okay. But only the thing is, the notation. But if you concentrate here, you will be familiar with this one. Okay. So we need to take the partial derivative of this cost function. Okay. We need to take the partial derivative of the cost function. So we call it dou by dou theta. Dou theta naught. So what is partial derivative? What is derivative, first of all? Derivative is nothing but slope, right? So derivative is nothing but a slope. What is slope? The rate of change. What is the rate of change? The slope can help us to find out the rate of change. That is what your derivative. But what is partial derivative? Partial derivative is when you use multiple variables, parameters, like in the case of multiple linear regression, right? So in the case of multiple linear regression, you will have more than one slope, right? So in that case, right, we need to take the partial derivative. So hence, I'm going to take the partial derivative on both sides of this equation. So here, theta naught comma theta 1. Okay, here theta naught is your intercept, this is your slope. Okay, and here what I do is, I'm taking the partial derivative on both side of the equation, dou by dou theta naught and into 1 divided by m, and sum of I equal to 1 to m, and the h theta of xi minus yi. Okay, and here what I do is, I just take this outside 1 by m into dou by dou theta naught into, we are left with h theta of x I minus yi. Okay, and okay, why we need to take this 1 by m outside of this one? There is something called scalar multiple rule. There is something called scalar multiple rule. Which is what it says is, if you take a dou by dou x of alpha and u, right, the alpha should come outside, alpha into dou u by dou x. Based on the scalar multiple rule, we just took this outside and then we did it like this. Okay, so this is nothing but your alpha, right? So alpha into this one, dou u by dou x. Okay, and the next step is the same thing, 1 by m into, next I'm going to use another a rule called power rule. Okay, I just explain you what is power rule. 1 by m I equal to 1 to m, and here what I do is, sorry, here we have the squared one. Okay, and this 2 will come in front of this one, 2 into h theta of xi minus yi into dou by dou theta naught into h theta of x I minus yi. Okay, here I'm using something called power rule. Okay, this is this one, how we got it, we use something called power rule. In this case, for example, here something called dou by dou x and u to the power n. The n will come in the front and u to the power n minus 1. Here in this case, u is the u to the power n, right? This n will come in front of the u, and you need to subtract -1 from this one, u into n minus 1, and dou u by dou x. Okay, this is the one. And the next thing is here I just take the 2 outside, 2 divided by n, and here I put I equal to 1 to m, and I simply put, since I took the 2 outside, we are left with h of x to the ith value of x and ith value of y. Okay, this is the equation. Okay, and here in this case, right, for example, dou by dou theta naught. In this case, h theta of your x, ith value of x and ith value of y. Right, so okay, what I will do is, here we don't have space, and okay, look here. So this one, right, I thought of writing it here. So this is the one, this entire thing will become 1 here. This one will become 1. Hence, you will get this value. 1 into this one, you will get this one. Now the question is how I got 1 here. So what is h theta of xi? I just write it here, because if I go back and forth, right, h theta of xi, this is the hypothesis linear equation. That's what I said. Theta 1 plus theta naught plus theta 1 x. This is the hypothesized linear hypothesis function. And what is h theta of x? Which is nothing but theta naught plus theta 1 x. You just plug in here. Okay, in this case, what will happen? Theta naught plus theta 1 x. Okay, theta naught plus theta 1 x minus y dou by dou theta naught. So in this case, right, so theta naught plus theta 1 is minus y. See here, instead of h theta naught, h theta of x, the right side of the equation, right, I just plugged in here. If I say, h theta of x, right, instead of h theta of x, if I say this one, it is correct, right? The h theta of x represents this one. Okay, so in this case, right, so in this case, what happens is, when you take the partial derivative, when you take the partial derivative with respect to theta naught, because here theta naught, right, when you take the partial derivative with respect to theta naught, all the values except the theta naught becomes constant, right? Except theta naught, rest of the values are considered as a constant, and the constant will be dropped. So we are left with only theta naught. So what value is multiplied with the theta naught? 1, right? So hence this part becomes 1. You understood? When you take the partial derivative with respect to theta naught, all the values except the theta naught, right, will become constant, and that one will get dropped. You are left with only theta naught. What value is multiplied with theta naught? What is the coefficient value of theta? You just think that way, right? What value is multiplied with theta naught? Theta naught into 1 is theta naught, hence it is 1. Similarly, right, I will write it here itself. If I go to the next page, it will not be here dou by dou theta naught. We are taking the partial derivative. So instead of, right, so next one is, similarly, when you take the theta naught is nothing but the intercept. We need to take the partial derivative on intercept. We need to take the partial derivative on your slope also, right? Okay, so in this case, right, the same steps are applicable for the the theta 1. Okay, but in the case of theta 1, what will happen is the same thing. Okay, I'll just write it here. This part, okay, this part, dou by dou theta 1 into h theta of xi minus yi. Okay, if you plug in this value here, dou by dou theta 1 theta naught plus theta 1x minus y. this one will become x to the power I. And then the x to the power I, you need to multiply with this one. So this is for dou by dou theta naught, into j of or theta naught. Okay, theta naught. Okay, this is for your partial derivative for your intercept. You got only this part. You got only this part. Okay, and right. So because this one will become one when you the same thing, right? The same equation will come for theta 1 also. 1 by m I equal to 1, 2 into h of xi. And in this case, if you take the 2 outside, 2 divided by m, I equal to 1 instead of minus yi. Here instead of dou by dou theta naught, dou by dou theta 1 will be there. This is the one will come there. Okay. So in this case, if you take the partial derivative with respect to theta 1, what will happen is all the values except theta 1 will become constant. It will get dropped. So except theta 1x, the rest of the markings is a constant. Hence theta naught and y. See here theta 1 and theta 1, right? Simple thing. And here the theta naught and see the theta naught and theta naught. Okay. So in this case, when you take the partial derivative with respect to theta 1, so whatever the values multiplied with theta 1, right? That one will be, you will get the output when you take the partial derivative. So when you take the partial derivative with respect to theta 1, all the values except theta 1x will get considered as a constant, or it will become a constant. It will be dropped automatically. The next one is you are left with only theta 1 and x, right? Theta 1 is multiplied with x, right? Hence when you take the partial with respect to theta 1, the value is xi. So to summarize, okay, and here the derivatives, the final derivatives are like this: dou by dou theta naught, j of theta naught comma theta 1. Here theta naught, okay, and is equivalent to, so you can the 2, you can ignore the 2, okay, because in the cost function we have 1 by 2m, right? So right, so in that case, the 2 divided by 2, it will get cancelled. 1 by m is equivalent to 1 to m and s theta of xi minus yi and dou by dou theta naught, sorry, dou by dou theta 1, right? Dou by dou theta 1, j of, sorry, theta naught comma theta 1 of your j, okay, is equivalent to the same equation, but it has to be multiplied with by xi, s theta of xi and y to the power I into x to the power I. Got it? This is what your derivative. And what is the update rule? Using this derivative only, we are able to compute the gradient. With the help of the gradient, the algorithm can find out the right direction. Okay. So now the update rule is for theta naught and theta 1, we need to keep changing the value for theta naught and theta 1 by multiplying the learning rate. Learning rate is alpha by dou theta naught. This is the one, j of theta naught comma theta 1. See, this is the one, right? The right side equation will give you the gradient. The right side of this equation will give you the gradient for theta 1. Okay, and alpha. And here, when you multiply the learning rate with this derivative term, right? And if you subtract this one from your current position, this is your current position. Okay, current position. You remember in the curve, right? The person was standing here. The current position, if you subtract the new value, right? When you multiply this one with the size, right? When you subtract this from this position, you will get to know what the next value for your step size, right? So your next value, what is the step size for the next one, right? From this position, you will get to know that. For that, you need to keep update. We need to update this value here, okay? And theta 1 minus alpha into dou by dou theta 1 into j of theta naught comma theta 1. So here they use this colon equal. That means, assign the value here. Okay. This is the one. So now what is the objective here? Objective of gradient descent algorithm. So minimize the cost function j of theta naught comma theta 1, right? This is what my cost function, this is the objective. And using this equation, we are able to get the derivative. When you plug in this derivative here, and then if you multiply that by learning rate, the step size, which is nothing but the step size. And if you subtract this from your, this is your current position. Okay, this is your current position. From your current position, if you subtract this, you will get the next position here. Okay, you remember, look at this one here, right? So to get to know the next position, you need to subtract this one from your current, you need to subtract the product of the learning rate and the derivative term from your current position. This is your next term. Okay, this is your next term, this is your current term, this is the thing for the theta naught. And theta 1 here, it is, you need to multiply with xi. Okay, that's all here. This is the one. So derivatives, and you have update rule, everything. Look here, everything is there in my document. You can, it's all, it's all printed in a neat way. You can see it there. Okay. It is not there in this. Okay, look here. This is the one. This is your current position. And from the current position, if you multiply, if you subtract this one, the product of the learning rate with the derivative time, you will get the next position. This is your next position. For each iteration, when you obtain different gradient, right? Obviously, you will get the new value for theta naught and theta 1. So with the newly obtained theta naught, theta 1, you can get the different predicted value, right? So you remember that iteration. Look here, I just go back and show you this one so that you should be able to remember it. This is the equation, right? So partial derivative for MNC. Why do we need to find out the partial derivative for MNC? Because we need to know the gradient, right? We need to know the slope. So once you know the slope, right, the direction or the gradient, right, next step is you need to take the product of learning rate by your gradient for the slope, and then you need to subtract it from your current position so that you will get the new position. So what will happen is in this loop, right, for first iteration, you have zero values. For MNC 0, initially it will be 0. Okay, but when it comes here, it will plug in the value, you will get some value for MNC. And then in the second iteration, what will happen is you will get the new gradient value, and then you will get the different values for MNC. For different values of MNC, you will get different predicted value. And along with that, when you compute the cost for each and every value of MNC, if you compute the cost, and that's what we have seen it, right? So, and when you print it, we should be able to understand in each iteration for this cost, what is the estimated value for your slope and intercept. Got it? It's pretty simple, right? You're able to understand with this one. Only challenge here is you need to find out the number of epochs. Okay, you cannot blindly use 1,000, or you cannot use blindly 200 or 10,000, right? So if you use more number of iterations, take a lot of time, especially when you work with huge volume of data. So you need to you need to choose some optimal value. This is a hyper tunable parameter, epochs as well as the learning rate, which I will discuss it later point in time, how to fine tune the hyperparameter values for this. Hope with this simple script, you should be able to understand how to implement the gradient descent algorithm in Python. And also you learned about the stochastic gradient descent also. In the case of stochastic gradient descent, it takes for each iteration, it takes single randomly sampled record. Okay, first iteration, it sample the single value, and then for each iteration, only one sample will be used. Right? In this case, what happens for each iteration, it takes the entire data. That is the overkill. Okay, it takes the entire data to compute the value for MNC. If you have 1 million record, the first iteration, the first step, right, from one step to another step, if you need to move, right, you just think about that, the hill story. Okay, the person move from one place to one step to another step. If he has to take the entire data and then compute this, it's a very expensive one, but it is very deterministic when you use the batch gradient descent. This is also called a vanilla gradient descent, and some people, they call it as a batch gradient descent, because we are taking, for each iteration we are using the entire data to compute the value for MNC, to compute the new value for MNC. Okay, and in the case of stochastic gradient descent, we are taking for each iteration we are taking for each iteration we are taking only one randomly sampled record. That's it. That is different, but the implementation is slightly different. And this plot, I will just check it out. Okay, and I'll just do it. That is pretty much about it. Okay, so the difference between gradient descent and stochastic gradient descent. We have something else called mini batch gradient descent. So in the case of mini batch gradient descent, we take subset of the data. We take, instead of taking only one sample, or instead of taking the entire data set for each iteration, there is something else, a mini batch gradient descent. In the case of mini batch gradient descent, as the name says, the batch, there also they use batch, but we will use just subset of the data. Okay. But if you know these two, it is sufficient, because this is more than sufficient. But in the case of neural network, there is something called back propagation algorithm. In that case, a gradient descent algorithm is used to minimize the cost. Hence, it is mandatory to know gradient descent algorithm. Okay. You just watch my video, and then what I will do is, in the previous session and current session, right, I will upload the data in the website, because we have some issue in uploading it there. Okay, in the website, you'll see if we we'll try to fix it the earlier, and then we will upload it there. Okay.